So we're now at our third and final part of case study ex4. And this time, we're going to take a look at some new mechanisms. This is going to take a look at the two-parameter version of create, which uses flux sync to create, multiply, and display big fraction objects asynchronously. And this particular example is going to apply an overflow strategy. And when I run it, I'll actually show a bunch of them. This is the one that we're going to start with. It also shows how to use mono operators, which we've seen that before. And once again, it uses the blocking subscriber. This time, however, we've made the blocking subscriber back pressure unaware again. So it'll generate data as fast as it possibly can, and we're going to deal with the fast pace by using overflow strategies to compensate for the publisher publishing faster than the subscriber can subscribe. So we're now back in Project ex4 in my GitHub repository, and let's go ahead and click on that. You can see this time we're going to focus on the third and final of the test methods here, which is called test fraction multiplications overflow strategy. And if we click on that, it'll take us to that method. And let's see what this is doing. So the first thing to note is that this method, very early on, creates yet another blocking subscriber. And this time, the blocking subscriber is going to, once again, be back pressure unaware. So it's going to blast the data out. It's not going to stop the publisher. The subscriber and the publisher will not coordinate. The publisher can publish as fast as it wants to. And the way we're going to do this is we're going to make the publisher publish S max fractions times 100, which is 1,000. It's going to try to emit 1,000 big fractions. The emphasis is on try. So what do? We come down here, we use the two-parameter version of create, and we're going to pass it the results of the emitter. What is the emitter? The emitter takes this count, and it's going to return a consumer to a flux sync. And you can see what it does. It's going to iterate from I equals 0, I less than count, which, by the way, is not a very reactive way of doing things, but it's good enough for this example. It's going to generate, essentially, count number of items. And every time it goes through that loop, it's going to make a new random big fraction that's unreduced. And then every 20 iterations, it's going to print out how much it's generated thus far. You'll see when we look at the results. It's a nice way to see what's been happening. And then as it makes those big fractions, those big random fractions, if it hasn't been canceled, it goes ahead and emits them. So that'll be sent upstream, or downstream rather. It'll be sent downstream towards the subscriber. And after we blasted out all count of these, which is 1,000 in our case, then we say we're done. So the question will be, do we actually get to be done or not? And it depends on the overflow strategy. And the overflow strategy we have to start with is the error overflow strategy. What we then do is we take this stream of big fractions and we're going to multiply them in parallel using our big fraction utils multiply fraction method that multiplies them by this constant. And then we subscribe the blocking subscriber and we await. So the interesting question is, what's going to happen when we run this program? And we'll see what happens when we run the program, because it's generating data faster than we can keep up with it. So here's what happens when we call this. This is the drop variant, or sorry, the error variant of this. So you can see that we start off, and wherever it says publishing items, that's the publisher noting how many items it's published. 0 to 20, 21, it should be 21 to 40. You know, it's basically publishing things in that range. Whenever the subscriber gets a chance to do some processing, it prints its results out. And these are going to be coming out of different threads. I should probably put the thread IDs in here as well. So you notice we're generating data a heck of a lot faster than we're consuming it. And as a consequence, after we reach about 256, which, by the way, is the buffer size that is done by default, it's a 256 element buffer, at that point, an exception is thrown. It's the overflow exception, which is not the same thing that Project Reactor tells us that it's going to throw, but whatever. So it throws the overflow exception, and the message says the receiver is overrun by more signals than expected because we have a bounded queue. And so we actually did process 3 items, but then our buffer resources got overrun. So we threw an exception. So that's what happens with the error strategy. So let's change strategies just for kicks. And to do this also and not waste too much time, let's go back over here and comment out the other two tests so we don't have to wait for them to run, because this test takes a little while to run. And now let's get back over here and let's change this. Let's say we change this to drop. So now we're going to drop. So what's going to happen here is when things go awry, we're going to go ahead and drop them. Maybe. There we go. OK, so now we're off to the races. This will take a little longer to run than the error one. The error one blew up pretty fast because we quickly overran the buffer resources. This one will take a little bit longer to run, but we're dropping stuff, so it shouldn't take too long. Right now, it's still compiling, and it'll start running here any moment now. And when it does, you'll see what happens. So notice what happens. We got a lot more results than we did with error. But you'll notice, and this is probably very indicative, we only got 256 successful completions of these processing. And that's because the buffer size by default is 256. So once the buffer was more than 256, the items were being dropped. So we did get more stuff. Didn't drop. It didn't blow up right away like the other one did. The error one did. The error overflow strategy did. But once we reached a full buffer, it just dropped stuff at that point. OK, now let's go ahead and change this to a different value, just for kicks. And let's go ahead and change this to latest. So latest is somewhat akin to drop in that it will drop stuff. But the difference is it'll keep the latest value. So it'll overwrite the value. So as they show up from the publisher, the latest value will be the one that is served. Whereas before, we could be dropping ones that were not the latest. And you'll see, again, the results, they're all random numbers, so it's hard to tell that they're different. But they would be dropping different things. And once again, we got about 255, 256 before things blew up, because that's the size of the buffer. So let's go ahead now and change this to buffer. So let's change the overflow strategy to buffer. Now, this one may actually take a little bit longer to run. And that's because what it's doing is it's going to take that burst of events that are published by the publisher, buffer them up to the point where we run out of memory, which we will not, because we only have 1,000 of these things. And then it'll let them play out. So it'll let the events, it'll let the subscriber process the events out of that buffer, out of that queue, until it's essentially drained it. And again, this may take a little bit longer to run because it's going to have to go through all 1,000 of them. But if we're patient, we'll see in a moment what it's going to do and what it should do, unless something very strange has happened in the last few minutes. Since when I ran the test earlier, it should print all the results out in whatever order it printed them out. So we'll get a chance to see how that looks. Like I said, this takes longer to run. There you go. So you can see all 1,000 computations completed successfully, even though it took a while. All right, the last thing we're going to do, and then we'll be done. This is just kind of for kicks. Let's change this to ignore. And if you start trying to figure out what ignore does, you're going to get all kinds of weird answers. I asked my good friend ChatGPT what ignore did, and it was completely confused and seemed to think it was going to do what drop did, but in some slightly different way. It was very unclear what it was saying. I think its description of drop was incorrect also. If what we see here is the same as the last time I ran this, which it may or may not be, when I ran this before, ignore also was able to buffer and generate all the results. Why it does that, I'm not exactly sure. So it's not really clear to me what ignore does different than buffer. It doesn't seem to do the same thing as drop. It doesn't seem to do the same thing as latest. The way it's described is it says, ignore any back pressure strategy. When you do ignore, it's like ignore it. So maybe that just goes back to the default. Maybe the default is to buffer. I'm not sure. But you can see it gets 1,000. So everything got through. So it seemed to behave exactly like buffer, which I found odd. So if anybody can figure out what ignore does by whatever means, I'd be very curious to know, because it is not clear at all to me from reading the documentation.